So here we have the derivative as a function, and so this is, now number one is from 2.7. Number two, though, is from 2.8. And notice the difference. We have x, a variable that can just take on any value. So we're not talking about a derivative as a point. We're talking about the derivative as an entire function that basically takes on the values of the slope of the original function at every point. And it's called the derivative because it's been derived from the original function. Yeah. And here's an example here where we take a function and it says use the graph to sketch the graph of the derivative. And I just want to point out some things about this function, about the slope of the function. The slope is 0 right here because we would say it has a horizontal tangent line. And here, okay, so we're right about here and here, the derivative is going to equal 0. The derivative is going to cross the x-axis, the graph of the derivative. Now, but in here, the slope is negative, right? This function's going down, so the derivative, the graph of the derivative will be below the x-axis. And then once again, one more 0 value. So again, around here, the derivative will cross the x-axis. So it's going to be crossing here, here, and here. And then after that, the slope is positive, so it'll be above the x-axis. Okay, so again, it starts out negative, below the x-axis. Then over here, it's positive, above the x-axis. And then negative again. So here, we've plotted that graph. Okay, so here's the original function. And sure enough, here are the x-intercepts of the derivative graph. And just like we talked about, negative is below the x-axis, and so on. So that's one of the things we're doing in this section. And here's one more graph of a function. It's derivative, the square root function. The slope starts out basically vertical, and then it gets a little smaller, but it stays positive. It's going up. And so over here, it's still positive, but not as big. And this graph is right here. And basically, the slope at 0, 0 of the original function, the blue line, is vertical. And so it's not defined. The derivative is not defined there. And hence, you see the asymptote here, the vertical asymptote. It never gets to 0. But that's a good example, a visual example. Now, you're going to see me use, for the most part, this notation, which, as we talked about, is f prime of x or y prime. But there are other notations, and this here, d over dx, is called, this is the differentiation operator, and that is just as valid as the other notation. It's because two different people started calculus: Isaac Newton in England and Leibniz in Germany, and they both used different notation. They both started calculus about the same time. And so even till today, we have different notations for calculus. And I like to write the y prime. Why? Because it's less writing. But you might have a teacher in another class that liked the d over dx notation. And so you want to realize that they're both valid notations. Okay, so now let's talk about this function here. And I think you may be familiar with this function, the absolute value function. And it's right here, of course. And where is it differentiable? Well, it's differentiable here, and it's basically y equals x, right, on this side. But over on this side, it's y equals negative x. So it's a straight line, so it has a slope. And we're not going to get into the derivation down here. But basically, the slope is constant. On the right side, it's positive 1. And the slope is also constant over here on the left side, negative 1. So we're going to have, it's like the derivative is going to be a piecewise continuous function, or piecewise function. Okay, so again, here is the original graph, and here is the graph of the derivative. Notice very different looking graph, and it's not defined at 0 when x is 0, and it's because there's a corner there at 0. So anytime a function has a corner like that, it's not differentiable at that point. It's continuous. So a function can be continuous but not differentiable. Differentiable is a little harder. It's a higher standard. And then, so that's what they're saying right here, number 4. If f is differentiable, so if it is differentiable, then you know it's continuous. It has to be continuous to be differentiable. But the converse is not true. So we say the converse, if you read it backwards, that wouldn't be true. In other words, if we said if f is continuous, then it's differentiable, that's not true. And we just saw an example of that with the absolute value. It was continuous, but not differentiable. How can a function, well, what I was talking about, here's the absolute value with its little corner, and we see some other examples here. Another corner in this function, okay? A jump discontinuity. So again, that's not even continuous. And so if it's not continuous, it's not differentiable. This function is continuous, but the slope turns vertical for a certain period, for a certain value of x, basically. And so just like we saw in the earlier example, when you have a vertical slope, the derivative is not defined. The derivative would basically have a vertical asymptote on that. It'd be going down to negative infinity on both sides of that. And finally, higher derivatives, we can take, not only the first derivative, but we can take the second derivative and more derivatives after that. And so you will either see the notation f double prime, okay, and that's what I'll see it. That's how I see it. Or here we have this, and that's not a squared thing. It's just the second dx dy. And here's an example in real life of a second derivative. So we talked about this the other day. So S is a position function, okay? And then you have the velocity, okay, is the derivative of S, the position function, because the velocity is the change in your location over time, or your change in your position over time. But we can also take the derivative of the velocity. The change in the velocity over time is called the acceleration. So the acceleration would be the change in the position. Or you could say the second derivative of the position. Acceleration, which is basically you stepping on the gas or you stepping on the brake if you're moving in a car. You're accelerating, you're changing your velocity. And then there's even a higher one, the third derivative that we have a name for. So the third derivative would be the change in acceleration. And that would be, well, basically, say you're at a stoplight and you want to just peel out of there really fast. Or somebody jumps in front of your car and you just got to slam on the brakes really fast. So that's the third derivative. It's the change in acceleration. It has a funny name. We call it the jerk, and it has to do with when you accelerate really fast or when you brake really fast. It's a very sudden movement, either way. And we can say we stop using little hash marks here for the fourth derivative. We just say f of 4, and for any other higher number, we just put a little number there. And so it's possible to ask you a question like, what's the 32nd derivative of a function? Bless you. So, yeah, that's it for that section.